Hello, welcome to another lesson of sectoral structures theory. This is related to the last video we've done. It's still within the same chapter, even though this is actually not mentioned in the book. But I thought it was a very interesting application of sectoral structures theory. So in the last chapter or in the last video, we looked at sectoral structures with a weight restriction on their parts, such that the restriction was the set 1 and 2, meaning that the weights of all the parts of the sectoral structure had to be either 1 or 2. And we found a very interesting pattern. We found that for the 1-2 set, the sectoral structures of even degree, so of degree 2n, had a size that was related to the Fibonacci sequence. So let me explain that one more time. So let's say we look at the sectoral set of degree 10, so all sectoral structures of degree 10, restricted to the ones whose parts have weights of only 1 or 2. And we found that the size of this set is exactly related to half of Fibonacci 2n plus 1 plus Fibonacci n plus 2. So this is for 2n. So very interesting relation that we find with the Fibonacci sequence. Additionally, for the odd degree, so if we have a sectoral set of degree 11, for example, so an odd degree, the total number of sectoral structures of degree 11 whose weights are restricted to 1 or 2 is also related to the Fibonacci sequence as 1/2 of f2n plus 2 plus f of n plus 1. And here we started with 2n plus 1 to mean that it's odd. So this is very interesting. And then when we do the calculation, we end up with the following sizes, starting with degree 1 and going higher. 1, 2, 2, 4, 5, 9, 12, 21, 30, 51, and so on. And again, this is directly derived from adding two Fibonacci numbers. Now we want to look at another restricted set. This time the restriction is more than or equal to 2. So we want the sectoral structures of degree n such that the weights of the parts are 2 or greater. In other words, if any part of a sectoral structure has degree 1, we exclude it. So we could alternatively say this is excluding sectoral structures with weights of 1. For example, let's look at degree 2. The degree 2 set that meets this restriction, we get only one sectoral structure, and that is 2 subscript 2. If we look at degree 3, we have also only one sectoral structure that meets this, and that is 3 subscript 3, because the other two don't meet it. So 1 cubed subscript 3 has a 1, and 2 1 subscript 3 has a 1. So again, the size of this is 1. If we look at degree 4, we have 2 sectoral structures, 4 subscript 4 and 2 squared subscript 4. Degree 5, we also have 2 structures. Degree 6 gives us 4 structures. Degree 7 gives us 5, degree 8 gives us 9, degree 9 gives us 12, and degree 10 gives us 21. So let's write those down. We see that we got 1, 1, 2, 2, 4, 5, 9, 12, 21, which is exactly the same sequence we saw earlier with the 1, 2 restriction, except it's shifted down or shifted up by 2 units. But it's the exact same sequence. So we took it, we moved it 2 places higher. So this is very interesting, because why should we get the same sequence when we are applying very different restrictions? If we look at the 2 sequences, here we have the degree, here we have the 1, 2 restriction, and here we have the 2 or greater restriction. And what we can quickly notice is that this same number that appears, for example, at degree 4 here, will appear at degree 6. So we moved it 2 places. If we look at 8, gives us 21. Here it appears at degree 10. So it's the same sequence. So we can say there is a rule that the size of degree n set that meets the greater than 2 or at least 2 restriction is the same as the size of the 1, 2 restriction for degree n minus 2. So we will say a restriction set of greater than or equal to 2 of n is equal to a restriction set 1, 2 of n minus 2. So a very remarkable relationship, and there's many of those, and there's many connections to the Fibonacci number, as we will see. So we can easily figure out the formulas for the size of the degree 2 or greater sets. So for the even degree, so 2n, the size of the set of degree 2n that meets the restriction of 2 or greater is equal to 1/2 Fibonacci 2n minus 1 plus Fibonacci n plus 1. Similarly, for the odd structure of the form of degree 2n plus 1 with a 2 or greater restriction, we get a very nice formula actually here. It's equal to 1/2 of Fibonacci 2n plus Fibonacci n. For example, if we want the size of the set of degree 6 with a 2 or greater restriction, it will be 1/2 of Fibonacci 5 plus Fibonacci 4, which gives us 4. So all is good. Let's look at this one more time here in terms of Fibonacci. Let's look at the size for a restriction of 2 or greater, such that the degree is 6. In this case, we said we will look at Fibonacci 4 and Fibonacci 5. So Fibonacci 4 is 3, Fibonacci 5 is 5, 3 plus 5 is 8, 1/2 of that is 4. And then we move 2 units or 2 places up, we get a 4 for the 1, 2 restriction at degree 4. Let's do another one. So let's look at the degree 9 for a 2 or greater restriction. For this, we will need the Fibonacci numbers of the 8th Fibonacci and the 4th Fibonacci. So that is 3 plus 21. That's 24. 1/2 of it is 12. Indeed, 12. And if we want its equivalent for the 1, 2 set, we just move 2 places up. So we have 12 at degree 7 in this case. So a very beautiful relationship arises. Now notice, if we want to think of group theory isomorphisms, then there's clearly a group isomorphism between the 1, 2 restriction set and the 2 or greater restriction set. the first of all, there is a one-to-one relationship, or there must be a one-to-one relationship between each element of the 1-2 set and a corresponding element of the 2 or greater set. And additionally, the combinatorial operation on each of these elements gives us the exact same result. So let's try to figure out what this relationship is. We will define a sectoral function R bar that takes us from the 1-2 restriction set of degree n to the 2 or greater restriction set of degree n plus 2. And we will define a sectoral structure or a sectoral operation R bar on the sectoral structure an to give us another sectoral structure B of a B subscript n plus 2, such that an has a 1-2 restriction and bn plus 2 has a 2 or greater restriction. Similarly, we will show that we will define R bar of an to be equal to G bar, another sectoral function, of the conjugate of an. And notice, if we didn't know what a conjugate is, if we didn't know much about sectoral structures theory, we wouldn't be able to figure out this isomorphism. So the conjugate of an. And then we will define G bar as, if we have a sectoral structure, G bar of that sectoral structure means you identify two parts that have the least weight and you add 1 to each of them. So for example, if we start with a sectoral structure an, what we do is first we take the conjugate of that sectoral structure, as we saw in a prior lesson how to do that. We identify the two parts that have the least weight, and if there's many of those, we will go to the ones that are closest to the L prime end to keep it as a one-to-one relationship. And then we add 1 to each of these two parts. So let's look at an example. Let's say we have an as the set actually with 1-2 restrictions of degree 5. An is not the set, sorry, it's the sectoral structure. But let's look at the set of degree 5 with a 1-2 restriction. And we know that if for degree 5, we should have 5 elements in that set. So these elements are 1 to the 5th subscript 5, 2 squared 1 subscript 5, 2 1 2 subscript 5, 2 1 cubed subscript 5, and 1 2 1 squared subscript 5. And I'll write them here as a set as well. Let's take the conjugate of each of these. The conjugate of 1 to the 5th is 5 subscript 5. The conjugate of 2 squared 1 subscript 5 is the same, it's a self-conjugate. And then 2 1 2 subscript 5, the conjugate is 1 3 1 subscript 5. 2 1 cubed gives us 4 1 subscript 5. And then 1 2 1 squared gives us 3 2 subscript 5. So these are the conjugates. Now we want to apply this G bar operator or function. So let's look at 5 subscript 5. We have 2 1s that we want to add, and we only have one place to add them because there's only one part. So this becomes 7 subscript 7. So now we've established a direct one-to-one relation between 1 to the 5th and 7 7. We'll draw a line between them. Next, for 2 squared 1 subscript 5, we add 1 to the part with weight 1, so it becomes 2 cubed. But we have an extra 1. We will add it to the part that is closest to the L prime end. So this becomes 3 2 squared subscript 5. And we will draw another 1-to-1 relation. Next, we have 1 3 1. There's 2 1s. We add 1 to each of them. It becomes 2 3 2. We have 4 1 subscript 5. So here there's only 2 parts, so we add 1 to each of them. It becomes 5 2 subscript 7. And then we have 3 2. Again, this is 2 parts, so this becomes 4 3 subscript 7. And what happens is we actually end up with the entirety of the set that is restricted to 2 or greater of degree 7. So this is a direct group isomorphism between the two groups. So this is pretty neat. It's not intuitive, it's not obvious at first, but this is part of the beauty of digging deeper into some of these restrictions, and many surprising relationships emerge. Thank you.